let's get this show on the road here. I guess I need to pull up a new one. Day before a reading break. Well, second day before a reading break. Thanks for coming, guys. We'll start with should we start with, let's start with the, I was gonna do it in different order, it's okay. Test 2 layout. So, right, because we've got our test 2 on Tuesday after the break, we'll have the break to work on it. And so test number 2 on Tuesday. And what is that? 23rd, 24th, 25th? And like I said last day, so I'll use the first kind of up to 50 minutes to answer any questions that you might have. Of course, if there are bigger questions, you should contact me throughout the break and kind of get those sorted out. You don't want to leave those until the 50 minutes before the test, right? And so up to 50 minutes before the test, will be used to answer questions. But then if there are no questions and you just want to get it over with, of course, we'll start. When there are no more questions, oops. No more questions, we will start the test. Right, so unlike last time where we had class after that test, then you'll just be able to leave. Okay. So for test 2, test number 2, the layout. And I'm not trying to trick you or anything, right? So for when I gave you the layout for test 1, that's exactly what it was. When I give you the layout for test 2, that's exactly what it's gonna be, right? It's just, I'm not gonna give you the functions, obviously, so that would not make sense. So question 1 is gonna take us back to the infinite limits. So it's gonna be an infinite limit question. Infinite limit question. So that's the limit as x goes to either positive infinity or negative infinity. And so I'll do plus minus infinity. Oh, maybe make it look like infinity. There. Of f of x. So if x is going to infinity, right, that's hard to plug in, but you have to figure out, okay, what's the behavior of f of x as x gets large? And it's only going to be negative infinity or positive infinity, right? So it's going to be one of the ways. And we're essentially figuring out if we're going to have a horizontal tangent line. Okay? So it's going to be an infinite limit. And off the top of my head, I can't remember what section that was. Anyways, you'll find it. Second question is going to be an intermediate value theorem question. Intermediate value theorem. We said that the intermediate value theorem is pretty obvious, right? If we want to show that this function crosses the x-axis, right, where the output is 0, then if we can figure out some input of x that gives a negative output and some input of x that gives a positive output, then by the intermediate value theorem, it has to cross and give a 0 output at some point between those 2 points, right? And so we're going to show that f of x equals 0 has at least one solution we did it 2 ways, right? We said, okay, well, first I'm going to give you the bounds, and usually what we do if we have bounds, then it's a relief, right? Because then we can just start at the lower bound, plug that in, see if we get a positive or a negative number, plug in the upper bound, see if we get a positive or negative number. If we get a positive here and a negative here, switch them up a bit, right? Then we're done. Right, because then by the intermediate value theorem, it has to equal 0 at some point between those. Okay? So it has at least one solution. It was a little bit harder, right, if we didn't have any bounds, so it just said has at least one solution, not on any range. Then we had to pick values of x and kind of try our way there. So a little bit harder if you don't have the bounds. But either way, the idea stays the same. Question 3 is going to be the limit definition of the derivative. So the limit definition of the derivative. Here, you're going to have to state the limit definition of the derivative and evaluate. Let me just had a little panicky moment. I'm not on mute. That's good. I get those about once a class. Except when I am on mute, then it doesn't hit me. The fourth question, right? And I've told you that all of these throughout as we're doing them, right? So the fourth question is when we give you a graph, right? And it can be any graph, and then you have to sketch the derivative below it, right? Which means you have to identify, okay, where are the maximums and the minimums, right? Where is the derivative going to be 0? Track those down onto the next graph, right? And then kind of go from there, figure out if it's going to be a positive slope or a negative slope, and reflect that in your graph of the derivative. So given a graph, sketch the derivative. Question 5 is just going to be to state the product rule, the quotient rule, and the chain rule, which we're about to do today, using prime notation. Right? So we don't have to use those differential operators. So state the product, quotient, and chain rule. And then finally, you're just going to be given 4 functions and asked to find their derivatives, right? And so that could be a combination of the product rule, the quotient rule, the chain rule, definitely, which we're going to talk about today because it kind of, opens up more possibilities for questions. And so just given 4 functions, find their derivative. You could use the limit definition of the derivative, but it's going to be pretty nasty. So you'll definitely want to use the differentiation rules. So use differentiation rules. And that's test 2. I'd say there's 4 things that you could just memorize and blah onto the page, right? The limit definition of the derivative, the product rule, the quotient rule, and the chain rule, right? So those are just going to be memorized, and then just, the idea being that you can use them later for the other problems. Okay. Any questions about test 2? All right. Then let's do a little bit of review, because we didn't quite finish all my examples, or we ended early because I wanted to use these for our review today. So we were talking about the product rule and the quotient rule, and did everyone get a copy of these differentiation formulas? Wait. You'll have to memorize these, but it's nice to have a summary. Okay. So, an example. If f of x equals x e to the x cos x, find f prime of x. So first, let's dissect this thing, right? Because what you're going to do from now on, if you're asked to differentiate things, it's going to be a couple of rules combined often, right? It's not just going to be the product rule or the quotient rule, or even just the chain rule. It's going to be a combination. So we want to be able to dissect this function and figure out what we need to do before we actually do it. So we've got f of x is x e to the x cos x. We've got a function, x is a function, right? E to the x is a function, and cos x is a function, right? And so we've got a product rule, product of 3 functions here. What we want to do though, because the product rule, we use it for 2 functions, but because cos x is its own thing, what I'm going to do is I'm going to pick off cos x and deal with that first. And then I want to have x e to the x. I'm going to treat that as 1 function for now. Okay. Treat x e to the x as 1 function for now. Because what we see here is, okay, if I treat x e to the x as 1 function, then I will have to take the derivative of it, and it will use the product rule, right? So I'm just going to smush it together as 1 thing for now. We are in the review, but if we have recall if f of x is f of x times g of x, or I guess we should call it capital F or something. So just restating the product rule, then f prime of x is f of x held steady times g prime of x plus g of x held steady times f prime of x. So you'll hold the first one steady, take the derivative of the second, and then hold the second one steady and take the derivative of the first, if you've got a product. So in our case, right, we're letting f of x be x e to the x, and then g of x be cos x. So we have to find f prime of x is going to be, well, f of x held steady is x e to the x. The derivative of cos x is negative sine x, and that's on your formula sheet, or not on the formula sheet, I shouldn't call it that because you don't get a formula sheet. It's on the handout that I gave you. Wait. And you do have to memorize all those, the trig functions at least. So that's the derivative of cos x, and now we hold cos x steady, cos x times the derivative, and I'm going to do d dx of x e to the x. And what I reacted to last day, because I didn't even really bat an eye, I said, oh yeah, nope. If you're using differential operators, then you don't want to combine them with primes. But then I was doing it kind of willy-nilly, and I looked, and the textbook also does it kind of willy-nilly. So you can combine them. So here, right, I've got f prime of x, but then I've got a d dx of x e to the x. And so, but the reason is because the d dx is just kind of clearer than saying x e to the x and then putting a prime out top, right? Because that's what you would do if you wanted to use prime notation. So you can mix and match, whatever makes it easier to communicate. And so now, right, just keeping an eye on this, this is another product rule that we have to use. So just writing out what we've got here, I've got x e to the x times negative sine x. I guess I could pull that negative outside, clean it up a bit. Negative x e to the x sine x, there, plus cos x, and then I'm going to put square brackets to square it off here. Holding x steady and taking the derivative of e to the x, but the derivative of e to the x is just e to the x, plus holding e to the x steady times the derivative of x. The derivative of x is just 1. But making sure that cos x is multiplying all of that, right? It's multiplying the derivative of x e to the x, which happens to use the product rule. So now we can expand and simplify a little bit here. And so we get negative x e to the x sine x plus x e to the x cos x plus e to the x cos x. If I wanted to, I could pull out the common e to the x, but I don't see anything else that I could pull out. But it might be nice. So e to the x times negative x sine x plus x cos x plus cos x. And I'm going to leave it there. on the test, right? Where you have to, that last question where I give you 4 functions and you have to differentiate them, it says do not simplify. Okay? So if you took it to even the second to last step here, I do want you to expand out that cosec, but if you take it to here, then you're done. Right? So don't spend any time simplifying. You could pull up the e to the x. I'm not going to deduct marks, but you don't have to, right? And so it make sure that you read that it says do not simplify, because you could go down this rabbit hole of, oh, I've got this identity or this identity. No. So. How about another example? If y is tan squared x, find y prime. Tan squared x, remember, is just tan x times tan x. And so if y is tan squared x, then y is also tan of x squared, right? Those are equivalent. And that's a key thing to keep in mind, which is just tan x times tan x. So now I'm at the product rule. Maybe you've got them memorized already, right? But the derivative of tan x is secant squared x. So by the product rule, we know that y prime is going to be holding the first tan steady, and I mean, because they're the same, it doesn't really matter, but tan x times, should I show it? Probably. I'll show this middle step, d dx of tan x plus tan x, which is now the second tan x, but it actually doesn't matter, times d dx of tan x. Puts us at tan x times secant squared x, right? Because the derivative of tan x is secant squared x, plus tan x times, again, secant squared x. Well, now I just have 2 tan x secant squared x. Any questions about that before we start the quotient rule? Ha, chain rule. We already did the quotient rule. No. Okay. Let's see where I've got a page break. I'll start this on a new page. Section 3.4 is the chain rule. So far, we've really only tackled, minor derivatives, e to the x, a constant, a product, a quotient. And so the chain rule is if we have something like, so consider a function like f of x equals the root of x squared plus 1. Even if you rewrote this as x squared plus 1 to the 1/2, we don't have a tool to deal with this, right? We can't really rewrite it as a product because it's to the power of 1/2. And so this is where the chain rule comes in. Okay? So we need to be able to take the derivative of, this is essentially a composite function, right? The square root function wrapped around x squared plus 1, right? So we've got a function inside a function. And so we need to be able to take the derivative of a composite function. And that's, in comes the chain rule. So what we want to do is we want to look at this, right? And here it's pretty obvious that we've got a square root function and an x squared plus 1. We could break it up as x squared as its own and 1 as its own, but we would just treat it as its own one thing, I would say, polynomial. So if we've got f of x is the root of g of x, in this case, if g of x is x squared plus 1. That's true. Which is f of g of x if f of x is the root of x. So therefore, f of x is f composed with g of x, right? A composite function. And you've got the chain rule on your handout. It's got the official version. But essentially the chain rule says that if f of x is a composite function, f of g of x, then the derivative of that function, f prime of x, is going to be the derivative of the outside, f, so f prime, and then just leaving g of x inside, times g prime of x. So this here is the derivative of the outside function evaluated at the inside function multiplied by the derivative of the inside function. I'll steal it from the handout just so we have them here. Copy. Right. Because this is the official version, right? But we've just got a summarized version. Often in my mind, if I see a chain rule situation, right, a function inside a function, then I just say the derivative of the outside times the derivative of the inside, right? Because I'll just ignore the evaluated at the inside function. And so I often summarize the chain rule oops, the chain rule as the derivative of the outside times the derivative, oops, times the derivative of the inside, right? Outside, inside. It's missing some components, but at least it's a reminder to me of what I need to do. So if I've got a function wrapped around another function, then I have to take the derivative of the outside, leaving the inside as it is, and then multiply it by the derivative of the inside. So let's do that one that we started with. So if we have to find f prime of x, if f of x is the root of x squared plus 1, it might be easier to say that, well, I can rewrite f of x as x squared plus 1 to the 1/2. Right? Because now I can just use the power rule. Right? Which is that we can bring that power out in front and then decrease the power by 1, and that's our derivative. Right? And so then f prime of x is going to be, well, I'm going to bring that 1/2 down, right? Because this is the outside function, holding the inside function steady. So x squared plus 1 to the power of 1/2 minus 1 times, and just to emphasize, should I do it? Should I not do it? I was going to do the d dx of x squared plus 1, but I might just go to 2x, right? The derivative of x squared plus 1 is just 2x. And so times 2x. And then I'll write little notes instead. So this is the derivative of the outside. And this is the derivative of the inside. So just like we did here, we can combine the chain rule with, and we have to combine the chain rule with all the other rules, right? We can combine it with the power rule. We can combine it with the product rule, the quotient rule. And so the chain rule is often used with other rules, such as the power rule up top, see previous example, the product rule, or the quotient rule. So let's do an example. Because now we're just going to do examples. till our hand falls off. No. But if we have to differentiate something like y equals x to the 3 minus 1 to the power of 100, right? Here we've got just the power rule on the outside, right? Something to the power of 100, so my outside function is that power of 100. So I can take the derivative of that, and then the derivative of the inside is just 3x squared, right? So now y prime is going to be 100 times x to the 3 minus 1. 100 minus 1 is 99, so to the power of 99 times 3x squared. Although, looks like I managed to forget the square in my notes. Because the minus 1 goes away. We can simplify this a little bit, right? But we're not going to spend a lot of time simplifying things because usually we don't really need to, but I can multiply 3 and 100 to get 300 and then pull the x squared outside and then x to the 3 minus 1 to the 99. And then I'll just leave it there. I don't know what else I would do anyways. Expand the power of 99. Ugh. Oh, thanks. Bless you. How about another example? Find f prime of x if f of x is 1 over the third root of x squared plus x plus 1. First thing you see, right, should be that quotient rule, right? You've got a fraction here, so right away you're thinking quotient rule, and then your next thing that you're thinking is, how can I avoid using the quotient rule, right? Is there some way that I could rewrite this so I don't have to use the quotient rule so that I can use something else, right? And so I've only got a power of 1, right? And so I could rewrite this as, right, I could raise everything in the bottom by putting it to the power of -1. And so what I'll say here, or I should use a different color. We could use the quotient rule but rewriting this so that we can use the power rule instead will be much easier. But rewriting this so we can use the power rule will be much easier. So absolutely you could use the quotient rule, but let's not. So what we're saying is we're going to rewrite f of x is x squared plus x plus 1 to the -1 over 3, right? The third root we can write as to the power of 1 over 3, and then to bring it up from that denominator, we raise it to the negative power. So now my outside function is something to the -1 over 3. So what I've got here is, okay, if I'm finding f prime of x, dealing with the outside function, the derivative of that is going to be negative 1 over 3 times, and then the inside just stays the same. X squared plus x plus 1 to the power of negative 1 over 3 minus 1. Just to show where all these numbers are coming from. Inside, I've just got a polynomial, so that's the power rule combined with the sum or the difference rule. And so now I've just got 2x plus 1 is the derivative of the inside. All I'm going to do here, I don't see anything else that I could simplify. I'll just simplify that power of negative 1 over 3 minus 1 to be negative 4 over 3, but that's about it. Negative 1 over 3 times x squared plus x plus 1 to the negative 4 over 3 times 2x plus 1. And I'm just going to leave it there. You could rewrite the x squared plus x plus 1 in the denominator, but I'm just going to leave it as it is. Any questions so far? More chain rule. You got it. How about we kick it up a notch? Find the derivative of the function g of t, which just means that the variable inside is t, so now we're going to be differentiating with respect to t, of t minus 2 over 2t plus 1 to the power of 9. Whoa. My outside function is x to the power of 9, essentially. Right? My inside function needs a quotient rule, right? Because I've got that quotient. I don't see any way that I could simplify this, right? Rewrite it as a polynomial. So I guess I'm stuck with the quotient rule, right? So here I've got a quotient rule inside a power rule. Right? You can think about it that way. So like I said, the first thing you're going to do for each of those functions is just figure out what the individual functions are, right, on the test when you have to differentiate those 4 functions. So the derivative of the outside times the derivative of the inside, if we write it as d dt, just to show off some notation here and just so we don't lose track of those differential operators, it's d dt because I want to differentiate g of t with respect to t because that's my variable inside, right? And so that's the only reason that I've got d dt instead. So the derivative of g is going to be the derivative of the outside, so 9, holding the inside steady times t minus 2 over 2t plus 1 to the power of 8. 9 minus 1 is 8. And then what I'll do to show that it's times the derivative of the inside, I'll do d dt of t minus 2 over 2t plus 1. So now, this is the derivative of the outside, and this is the derivative of the inside. Right? The derivative of the outside times the derivative of the inside. we're done with the outside, right? So that outside, we're done. We can focus on the derivative of the inside, which is now going to require a quotient rule, right? But we can keep 9 times t minus 2 over 2t plus 1 to the power of 8 times, and I'll put it in big square brackets just so I can keep track of what's what. All right, the quotient rule says that, okay, it's g times f prime minus f times g prime over g squared. So g in this case is 2t plus 1 times the derivative of t minus 2 with respect to t is just 1 minus f, which is t minus 2, times the derivative of g, which is just 2 with respect to t, of course, over g squared, which is 2t plus 1 squared. Okay, we can simplify this a little bit, right? Only to clean it up. But as soon as you're out of brackets and just kind of multiplying things cleanly, then I would say that you're done. So we have 9 times t minus 2 over 2t plus 1 just to the power of 8. That's just held steady. I can clean up this quotient here, and so I've got 2t plus 1 times 1, nothing happened. And then expand, well, I can bring in the 2, so I've got 2t minus 4, and then bring in the negative. So then I've got minus 2t plus 4 over 2t plus 1 squared. This is going to simplify a little bit, right? 2t minus 2t goes away. And then I've got 1 plus 4 in the numerator. But also, I've got the 2t plus 1 and 2t plus 1 to different powers. So what I'm going to do is I'm going to work at trying to consolidate those because I actually can collect those in the denominator, right? And so what I can do is I can rewrite this as 9 times t minus 2 to the 8 over 2t plus 1 to the power of 8. I'm allowed to do that because as long as I bring it in, so as long as I'm multiplying or dividing, I'm allowed to bring that power inside. I just can't bring the power of 8 onto 2t plus 1, right, because it doesn't work that way. But now we've got 5 over 2t plus 1 to the power of 2. I can combine 9 times 5 makes 45. And then I've got times t minus 2 to the 8. Nothing's going to happen there. But I can combine my 2t plus 1 to the power of 8 times 2t plus 1 to the power of 2, right? I've got the same base, so I'm allowed to add those powers. And I get over 2t plus 1 to the power of 8 plus 2 makes 10. And that's it. Yeah.
On the test, would you have to simplify to the last step, or could you leave it?
Well, where could we cut it? I'd want you to go to at least that second to last line. But then it's so tempting, right, to combine that 2t plus 1. So because I do want you to simplify this up here, right, the quotient rule, I want you to simplify as much as you can. But then sometimes or often, right, we're not gonna have the same thing here and here. And so necessarily, unless we're just plain old quotient rule, then it'll work out. But I probably would say, yeah, you could probably go to here, maybe. But then it's so tempting that you just combine them. I know that one was a little bit much, but it's what we have to do. So let's do another one. Example. Differentiate y equals 2x plus 1 to the power of 5 times x to the power of 3 minus x plus 1 to the power of 4. First, let's dissect this thing, right? Because now, well, it looks like I've got the product of two powers, right? And so now I've got an inside function and an outside function, right? So I've got the chain rule times the chain rule. So you're gonna have to break this up, right? Because you've got a product rule of two chain rules. So I'm gonna let you work on this one for a little bit on your own to see where you get to, and then we'll go through it together, of course. So if we start kind of dissecting this thing, right, we've got y. I'll just rewrite it here. 2x plus 1 to the power of 5 times x to the 3 minus x plus 1 to the power of 4. My hands are all slippery because my hands are so dry, so I was moisturizing them. Big mistake, my slippery pen. So here, right, I've got, I'm going to need a chain rule here. And here, I'm also going to need a chain rule. But because I'm multiplying two chain rules, right, overall, I'm going to end up needing a product rule. So I'm going to start with the product rule because the product rule is going to lead me to these chain rules. So, and I'll give myself lots of room, kind of spread it out to the page here, or the edge of the page. dy dx, or d dx of y, it doesn't matter, is going to be, okay, let's use the product rule. And so that means I hold the first one steady. So 2x plus 1 to the power of 5. And then I'll just use d dx of x to the power of 3 minus x plus 1 to the power of 4. Plus, then the second one is held steady, x to the power of 3 minus x plus 1 to the power of 4. And then d dx times the derivative of this first, which is 2x plus 1 to the power of 5. So here's that chain rule again. I guess I'll use matching. So here's why I said we would end up at the chain rule anyways, right? Because there you would have the chain rule. And so we start from the very outside and then we work our way in, right? So if the outside, if the whole grand thing is a product rule, then we start there and then the chain rules will just kind of fall out. But overall, oh, got a page break, so I'll just scoot this up one line. Wait. I'm looking at the product rule here. Okay. So for these things, you definitely you want to take it nice and slow, keep your wits about you, right? Holding things steady and moving through it methodically. Can't really do anything methodically without a lot of practice. So definitely take some time to practice and just kind of pick random things, try to identify what you need to do in there, and then go for it. All right, so now that outside 2x plus 1 to the power of 5, I can just hold steady now. And the derivative of x to the 3 minus x plus 1 all to the power of 4, well, that's going to be times 4 times x to the 3 minus x plus 1 to the power of 3 times the derivative of the inside, which is going to be 3x squared minus 1. I'm going to throw just big square brackets around here just to indicate that that's the first chunk, and now I'm dealing with the second chunk. And I know I'm going to run out of room, so I'm just going to put it over here, down here. Plus, keeping that x to the 3 minus x plus 1 to the 4th steady. And then we've got that chain rule, so now I'm going to times it by 5 times 2x plus 1 to the power of 4. Oops, plus 1. I'll sneak it in better. 2x plus 1 to the power of 4 times the derivative of the inside there, which is just going to be 2. Notice when I run out of space, right, you're always stacking your equal signs, but also if I run out of space, I don't put the plus right up to it. I indent it a little bit just to show that, hey, this line is actually continued. So that's one way that you can make it a little bit neater. All right. There's no more derivatives that we have to take, but we do have to simplify this just a little bit, right? Just until there's no more extra multiplication or addition in there. So here we go. We can focus on first, I'm calling them chunks. I don't know. I think of them as chunks. First chunk here is, what can we do? We can pull the 4 out front, but nothing else really, unless I want to expand, which I definitely do not. So how about the second chunk? Looking at this, I can pull out 5 times 2 in front, but also looking at the combination of the two. So maybe I'm gonna just skip that step, because looking here, right, I've got a coefficient of 4, I've got a coefficient of 5 and 2, right? So I've got a common factor there, but I've also got a common factor in 2x plus 1 to the power of 4 or to the power of 5, right? So I can pull out 2x plus 1 to the power of 4, but also in the x to the 3 minus x plus 1, I've got a common factor to the power of 3, right? And so here, and if you don't see it, I would just leave it, it's okay, right? But what we've got here is we can say, okay, well, we've got a common, and I'll move these, common, and what did we say? 2 times 2x plus 1 to the power of 4, and also a common x to the 3 minus x plus 1 to the power of 3. So what I'm going to do is I'm going to rewrite this and say, okay, well, I've got that common 2 times 2x plus 1 to the power of 4 times x to the 3 minus x plus 1 to the power of 3. And then everything else, right, times, still need a 2x plus 1 in that first one. 2, I'll put the 2 out front, I'll sneak it out front. Or maybe I won't. Don't want to get too messy here. I've already taken care of the x to the 3 minus x plus 1 to the 3, but I need the 3x squared minus 1. And then in the second chunk, I pulled out the x to the 3 minus x plus 1 to the 3, but I need the fourth one plus x to the power of 3 minus x plus 1. And then I've got the 2 taken care of, but I've also got times 5, and then 2x plus 1 to the 4 I already pulled out. So that seems to be it. There's not much else we can do. I'm just going to pull those coefficients out front and try to clean it up a little bit here, see what happens. And so this 2 times 2x plus 1 to the 4 times x to the 3 minus x plus 1 to the 3. Let's see here. Got a maximum of 3 terms. I can expand this. 2 times, so I've got 4x plus 2 times 3x squared minus 1 plus 5x to the 3 minus 5x plus 5. Squeezing it onto one page. Because I can expand the 4x plus 2 times 3x squared minus 1. It looked bad, but then once I kind of had a look here, so then we've got 2 times 2x plus 1 to the power of 4 times x to the power of 3 minus x plus 1 to the 3. Well, 4x times 3x squared puts me at 12x to the 3. Yeah. 4x times negative 1 minus 4x plus 6x squared minus 2. And then plus 5x to the 3 minus 5x plus 5. Keeping that outside the same, 2 times 2x plus 1 to the 4 times x to the 3 minus x plus 1 to the 3. 12x to the 3 plus 5x to the 3 puts me at 7x to the 3. Negative 4x minus 5x. Oh, let's deal with the x squared, sorry. Because we always want to write them, or as much as we can, we want to write them with decreasing powers, right, our polynomials. So we start with our highest, and then we deal with the decreasing powers. I didn't see the x squared there. So plus 6x squared. And then minus 4x minus 5x puts me at negative 9x. And then negative 2 plus 5, I'm at plus 3. There. Any questions about that one? When can you stop simplifying? Oof. This was a biggie, but once you pull out that common factor, not too bad. I don't know where you would stop reasonably. I mean, I guess you could stop there, but then you would probably see those common factors, and then you would pull them out anyways and just kind of go from there. Let's do a more mellow one. Example, if we have to differentiate y equals e to the sine x. You've got e to the power of something, and then sine x is essentially your inside function. The derivative of e to the x is just e to the x. So e to the x evaluated at sine x, that's going to be one of those where it puts us at e to the sine x. So it just becomes itself times the derivative d dx of sine x, which is cos x. So y prime is e to the sine x cos x. There, that's more reasonable because now we're done. So it doesn't have to be this long, huge thing. Let's talk about how we differentiate an exponential function. So put it on a new page, but to differentiate an exponential function, remember, is something like b to the power of x, where x is in the power, versus a power function where x is in the base, right? X to the power of a, let's say. So an exponential function, x is in the power, and a power function, ironically, x is in the base. These behave very differently, right? So it's important that we keep track of. So now we're talking about an exponential function. We already talked about how to differentiate a power function. Right? Then we just bring that a down. So then we get ax to the power of a minus 1. Right? And that's the derivative of that, nice and easy. But if we're talking about an exponential function, then we use the chain rule. I'll just specify that this is for any base greater than 0. So no negative bases, but I mean, that's always going to be the case for us. Let's see here, because I don't see how we're supposed to deal with b to the x with any of the rules that we know, right? And so what we need to do is we need to rewrite b to the x. And so we need to rewrite b to the power of x. Well, b to the power of x, we can rewrite as, and usually if you've got x in the power, right, the solution is going to involve a log of some sort, right? Natural log is kind of our go-to, right? So ln, and if I rewrite b as e to the power of the log of b, well, e to the power of the log of x is just x, right? So b, same thing. So e to the power of the log of b times x. Since e to the log of x is x, right? E to the log of b is b. So now I've got b to the x, I've rewritten as e to the log of b times x. So b to the x, just to summarize, is e to the log b times x. Well, the derivative of this thing with respect to x, right? Because now I've got e to some function, and the inside function is log b times x. Well, log b is just a number. I say log, but I mean the natural log, of course. Just kind of old habits. Because once you're in this course, the only logs that you're really going to care about, unless you go into engineering and stuff, they work in log base 10, but we're going to use the natural log. So now I've got e to the power of something. So now I can use the chain rule, right? Just remember that log b is just a number. So now you've got, essentially you can think of it as log base e to the 2x, right? Log base b is just the coefficient, or log b, sorry. So then d dx of b to the x, oops, is also d dx of e to the log b, b of x, or times x rather. Wait. This requires the chain rule. The outside function is e to the x. So now I've got e to the log b times x, the outside, the derivative of the outside evaluated at the inside, times, and I'll do it nice and slow, d dx of log b times x. But remembering that log b is just a number, right? The derivative of 2x is just 2, so the derivative of log b x is just log b. So now we get e to the log b x times log b. Okay, clean up this b here. Oh, looks the same. Oh well. Now I'm gonna undo what I did. E to the log b of x, or times x, I can rewrite as just b to the power of x. By the same argument, right? That e log b x is just b to the x. And so what I get is b to the x times the log b, the log of b. So as a rule, d dx of b to the x is just going to be b to the x log b. Because we've established that you're allowed to just use it, does mean that you have to memorize it, so you can, but you can always arrive at it using this little proof. But because we've shown that that's true, then you can just use it and it's fine. But if you don't feel like memorizing it, this is how you would arrive at it. Any questions about that one? So far we've only talked about the chain rule with 2 functions, but of course we can extend it to many, many functions, hence the idea of the chain rule. So you kind of start from the outside and then work your way in. So we've got this chain, and so we can extend the chain rule to more than 2 functions. Suppose that y is f of x, so a function of x. Oops. Oh, sorry. A function of u is what I wanted. F of u. And then u is a function of x, there, g of x. And x is a function of t, h of t. y is a function of u, u is a function of x, and x is a function of t. So now, right, I've got h of t inside g inside f if I want to talk about y with respect to t. And so then we can compute the derivative of y, with respect to t by saying, okay, well, if I want dy dt, the derivative of y with respect to t is how we read that. Well, that's going to be dy with respect to u, du, And then the chain rule says that, okay, but you've taken the derivative of y, that's the outside with respect to u, but now u is its own function with respect to x, and so now you have to take du dx. But also x is a function of t, so now to get to t, you have to take the derivative of x with respect to t, so dx dt. So here, boom, boom. I guess it's just two. Boom, boop. That's where the name, the chain rule comes from, right? Because we're just going from one to the other, right? So from dy du to du dx, dx dt, and then you can keep going, keep going, keep going. So let's do an example. If we have to differentiate f of x is sine of cos of tan x. Close the tan, close the sine. Closed, closed, good. Counting brackets. So now I've got sine as my first outside function, but then inside I've got cos wrapped around tan, so then I have another inside function, tan x, and then tan x, well, that's my final function, right? And so we're going to work our way from the outside in, and so we get f prime of x is, well, the derivative of sine is cosine, so cos, and then evaluated at the inside is just cos tan x. Times the derivative of the inside, which I'm just going to rewrite as d dx of cos of tan x. Because now I've got another chain. Chain, chain, chain. Also, the chain rule always makes me chuckle because I used to have math parties at my place when I was in undergrad and grad school. And so all the math people would get together and we would have derivative offs. So you just open up the textbook and then find the derivative of this function. And then it's timed, so everyone just does it, da 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 da. And then, of course, we're drinking. So it gets a little bit weird. But so everyone's doing their derivative, blah, 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 blah. And then my friend Melissa, she's super competitive. And so, and she has her PhD in math now. She's very mathy. But she throws her pen out, she's done. And then my friend Julie was the judge. And she's like, that's not right. And then, so Melissa's like, what's wrong? And so Julie's this timid person. She goes, you forgot the chain rule. Melissa, where? Everywhere. So don't forget the chain rule. Anyways, so the chain rule always makes me chuckle because I think it's really funny. All right, so don't forget the chain rule. Okay, more chain rule here. Leaving the cos times cos of tan x on its own because that's done now. Cos of tan x times the derivative of cos, which is negative sine, leaving the tan x on its own on the inside, times the derivative of tan x, which is just going to be, well, should I do d dx of tan x? No. I'll just do secant squared x. I just did it. Can simplify this a little bit, but only by pulling out that negative, I would say. That's the only thing I see. So what I'm gonna do, I'm just gonna pull out that negative and then cos of tan x times the sine of tan x times secant squared x. And that's it. So something reasonable like that, right? A simplification like that, even when it says do not simplify, right? Pulling out the negative is fine. And that's more what you'll probably see on the test. How about we do a last example? Differentiate y equals e to the secant of 3 theta. So again, we've got this e and then secant 3 theta on the inside. So dy, what's it going to be here? My variable is theta, right? So then I'm going to write dy d theta. So you always just differentiate with respect to the variable. If I had find dy dx of this e to the secant 3 theta, well, there is no x, and so it would go to 0, right? The derivative of this would be 0 because there is no x. But with respect to theta, we're going to have e to the x is just the derivative of e to the x is e to the x. And so evaluated at the inside function, well, that's just going to be itself e to the secant 3 theta times d theta of secant 3 theta. That outside is done. E to the secant 3 theta. Just leave it as it is. The derivative of secant x, let's say, is secant x times tan x. But then I've got the 3 theta on the inside still, right? And so I've got another chain rule here. And so I've got times secant 3 theta tan 3 theta d theta of 3 theta. Which puts me at e to the secant 3 theta times secant 3 theta tan 3 theta d theta of 3 theta is just 3, which if I want to simplify a little bit here, 3 e to the secant 3 theta times secant 3 theta tan 3 theta. Any questions? No. Okay. Then that's all I've got for today. I felt like we were going to be doing examples for, I guess we're not ending that early, but before reading break, hopefully you guys don't mind having a shorter class. So just remember, we've got that test on the Tuesday back. Chain rules, product rules, quotient rules, and a little bit from before, right, the limits. Any questions before we go? All right, have an awesome break. If you have questions when you're studying, then just get in touch with me. I'll be in Ottawa, but just text or email me, it's fine. Enjoy your break. See you on the other side. Bye, guys.